So now we've got three laws over here. We've got Boyle's law up here. We've got Charles's law, and we've got Avogadro's law. Now notice that they're all kind of related in a certain way. If I look over here and I take volume, what I'm going to do is I'm going to swap the V and the P for Boyle's law. So V is now proportional to KB 1 over P. So now volume is related to everything that we've got in these three laws. So let's combine them because we can, because, math. All right, so let's look at this. All right, volume is proportional to K times B. I'm going to leave some space here. And 1 over P. Okay? V is also proportional to Kc. Let me go ahead and put that in green. Why not? Because colors. Kc here. And this is times T. Good. All right. Now let's get at the Brown law. All right, over here. Ka. Right? And we're going to multiply this by n. Right? So let's rewrite this so we can see it a little bit better. So V is going to be T times N over P times 3 constants. And if we take these 3 constants here, we take KB times Kc times Ka. All of these constants, since they're constants, all they are numbers. If I multiply all 3 of the numbers together, I'm going to get another constant. So what I do is I do that. I take this number, right, multiply these 3 together, and what I get is a new constant. I'm going to call that R because I'm a pirate. R, right? So this constant is called the ideal gas constant. Okay? The ideal gas constant is one of these constants that is vital to everything that we really tackle as far as gas laws and everything else, right? Because it shows up in everything. This little gas law, because a lot of these guys drive the same thing from everything else. So gas law naturally is going to show up in everything else. All right, so this is the ideal gas constant, and it's a function of all 3 of these things combined. All right, now the ideal gas constant, let's see, right, has 2 different numbers associated with it. Okay, and the numbers that we have for ideal gas, right, equals, I'm going to make sure I get these numbers right. Right, gas constant value. There it is. Okay, good. All right, it comes in several different forms. All right, well, and I'll talk about that here in a second. Okay, I'll give you the numbers here in a second. But first, I'm going to give you, there's an R, right, and I've got this form. So I'm going to change this form into R here. Okay, so I'm going to rearrange this so I get rid of my fraction. And what I'm left with here is an equation that has PV equals nRT. And this is the gas law. Matter of fact, it's the ideal gas law. And it's important to identify it as the ideal gas law because there's a couple of assumptions that are built in here to make sure that this works. Okay? So PV equals nRT. We're going to put this over here because it's important. Ideal gas law. Hibner. Okay? Now, the ideal gas law gives us the ideal gas constant. So when we multiply all of those constants together, we get R. And R has several different numerical values. Okay? The first one is that, okay, the units that are associated with this are liters times atmospheres over moles times Kelvin. Okay? And remember, Kelvin here is interchangeable with degrees C, okay? But because it's a gas law is kind of thermodynamic, we like to use Kelvin in this case to avoid running into those negative numbers. So stick to Kelvin here. Now, if you notice, over here, this is R. If I rearrange my gas law so it's R, PV over NT is equal to R. Notice that, okay? Volumes, liters, atmospheres, pressure, moles, Kelvin, all right? So this form is what we use often with the gas law because that's the units that we get out for that. So 0.08206 liters times atmospheres over moles times Kelvin, okay? R also has a couple of others. When we start doing some mathematical manipulation to this R value, all right, we get a couple of others. The next big one that you're going to run into, 8.314. And what this is a representation of energetics, okay? And this is joules over moles times Kelvin. That means that there's a relationship between liters and atmospheres, okay? And there is, if you think about it, because there's force there. Whenever you have force, there's an energetic value there. So this particular value deals with energy, okay? There's a couple more, right? Since I've got joules, I'm going to have calories in there somewhere, right? And this one is 1.987. And this is calories over moles times Kelvin, okay? All I did was divide that number by 4.184, okay? And that gives me the value for calories, all right? And since I'm dealing with pressure and volume, I can throw newtons in there too, all right? Or in this case, pascals. So what I get is 8.314. This is meters squared times Pascal, meters cubed. There's a volume term. Meters cubed times pascals, again, moles times Kelvin, okay? And there's one more, right? And this one is, what is that? 62.36. And this is liters. No, wait. Get liters times torr over moles times Kelvin. Notice that in each of these cases, everything is over moles times Kelvin. Okay? Moles times Kelvin. But the top changes. Now, you notice that here, meters and pascals, meters cubed. Okay, meters cubed, volume. Pascal, pressure. PV equals nRT. Okay? Over here, liters times torr. Torr is a measurement of pressure. Okay? Torr itself times liters, so pressure times volume, same thing. Okay? And these two are energetics. What are the most important ones? Which ones do we have to know, Dr. Wayne? I know this is you're all telling the video. Okay, don't relax. I'll tell you here in a second. Jeez, no reason to touch the shaft of the computer. You're looking like a fool. Okay? The important ones to know, all right, these two. These are the two important ones to know. And for gas laws, the one that we're going to use the most is this guy. Okay? So there you go. There's the gas laws that you need to know. Everything you need to know about ideal gas laws. Now hold on. There's more about gas laws, and we're going to mess around with it here in a second. Okay? So stay tuned.